I'm gonna start this video lecture by recalling the following concept. So when you have a natural number n, we have this notation: S of n is the collection of all the permutations on the set 1 to up to n. So what that means is, remember, a bijection or a permutation is a function from the set 1 through n through the same set 1 through n. Remember, with that bijection we call it just a permutation on that. So this notation here, Sn, is the collection of all those functions. So if you don't remember well that concept, I'm gonna put the link in the video description of this video, so you can go and review that if you need to. All right, so let me give you another example here for another type of permutation. So let's suppose that our set A is 1, 2, 3, and 4. So we can define a function from A to A, which is going to be here a bijection, or we also call it permutation. Any bijection from a set into itself is called a permutation. Now, one way to define the function is by doing this graphically, like this. Of course, this is not going to be a good way to do it if you have a lot of elements here. So this kind of graph will only work if this is small enough to do a graph. So in this case, it will work. So here the graph, I'm going to put the domain here, which is 1, 2, 3, 4. And the codomain, which is the same thing. And I'm just going to indicate the name of the function here, alpha, and then we're going to say what the function is going to do. So alpha of 1, in this case, will be 1. Alpha of 2 will go into 4. Alpha of 3 will go into 2. And alpha of 4 will go into 3. So that's the way we define graphically. Now, if you want to write down that in a more specific way, so you just say alpha of 1 is 1. So 1 goes to 1. 2 goes to 4. So alpha of 2 is 4. And so on. Alpha of 3 will be 2. And alpha of 4 will be 3. So this is another way to define the function, this one or this one. Of course, this only works if the set A is small enough. In this case, the way we define the function, if you can see this is a bijection. So it's 1 to 1, and it's onto. All the elements here come from some element in the domain. So this is a bijection, which means it is a permutation because it's a permutation on the set 1, 2, 3, 4. Then we say that alpha in S is an S4. Now remember, S4 is the collection of all permutations on 1, 2, 3, 4. So the elements of S4 are functions. So alpha is a function, alpha is an S4. Now, one way that we can also represent a permutation in S4 or in Sn and in Sn is by an array. Now, what do I mean by an array? So instead of drawing a picture here for the definition or making the list on how do you define the function alpha, the bijection, instead of doing that, we're going to do this in an array form. This is just a representation of the function. So it's a way to write it down. Probably easier to do this than the other two methods. So the way we're going to do it is like this. You're going to start with, say, alpha equals, but in reality, this will be a representation. So this first row will always be the elements of your set 1, 2, 3, 4 in order. So the elements of A, your domain. And the second row here is going to be what the function alpha is going to do to each particular element. So in this case, for this alpha, alpha of 1 is equal to 1. So that I'm going to indicate that here. So alpha of 1 goes to 1. For the second part, alpha of 2 goes to 4. So 2 goes to 4. So we're going to indicate that here 2 goes to 4. Same do with the other one. So here alpha of 3 gives me 2. So I'm going to indicate that in the array alpha of 3 is 2. And finally, alpha of 4 is 3. So we're going to put 3 here. So that's going to be 3. So this is another way to represent the same thing. Again, all of these things are representations of that bijection. So this is a way to represent. So this is a little bit shorter, of course, than making all this list here or just looking at the picture. So actually from now on, we're gonna represent any permutation or any bijection in this array form. All right. So let's practice this notation a little bit more. Let's look at this example. So let's say we have S3 with composition. Remember, S3 is by definition all the permutations on the elements 1, 2, 3, which what I say here is the group of all the permutation on the set 1, 2, 3. And this binary operation is composition of functions. Remember that this, as we saw from the last video, this is a group, the group of all the permutations on 3 elements. So what we're gonna do in this example is this: list of the elements of S3 in an array form. So this is what we're gonna do: list the elements. Now, because this is a group, we already know that it has the identity, and if you looked at the previous video, which I'm gonna put in the video description, is the function that is the identity function, the function that does nothing. So I'm gonna start with that one first, and we're gonna represent everything in an array form. So in this case, if I'm gonna look at the identity here, it's gonna be a function that's gonna act on 1, 2, 3 because we are in S3, and the function does nothing basically. So the function, what it's gonna do, 1 goes to 1, 2 goes to 2, 3 goes to 3. That is the identity. So the function does nothing to the elements. And then we're gonna keep doing this type of thing with the array to see what the function, how many functions we get here. So one of the purposes of this example is to find all of the elements of the group. Let's look at the next one. So same thing. So we start with an array representation. I'm gonna call this one alpha 1. Same thing 1, 2, 3 because it's an S3. And so we're gonna now draw or write all the possibilities we can put here for this second row. Now one thing we wanna do is we're gonna keep 1 to 1. You don't have to do it, you can say 1 goes to 2, but let's do it this way. So let's take 1 to 2, and let's say 2 goes to, for example, 3. And then if that's the case, you don't have any other choice but to put 3 going to 2, because you cannot make 3 going to 1 because that won't be a bijection, and 3 cannot go to 3 because it's already here, so it will not be 1 to 1. So 3 will have to go to 2. So that will be one possibility. Now what else can we do? Another thing we can do is, let's say now we can say, for example, so 1 goes to 1 here. We did that one already. 1 goes to 1 here. Let's say start, for example, saying that 1 goes to 2. So if 1 goes to 2, I cannot put 2 here anymore, because if I do that, then that would mean that I don't have a bijection. So if I put a 2 here or a 2 in this position, I won't have a bijection. So the only numbers that I can put in this position and this position are 1 and 3. So we can make one choice here. So for example, 1 and 3. So for this particular element of the permutation, 1 goes to 2, 2 goes to 1, and 3 goes to 3. Now we can keep doing the same thing. So for example, 1 goes to 2, and instead of making the choice 1, 3, then you could be 3, 1. So that would be another choice that we can make here, 3 and 1. Right. So we have our third element, fourth element actually, because we have 1, 2, 3, and 4 element. So 1 goes to 2. Now we cannot make again 1 goes to 2 because we have only 2 choices here. So now let's say 1 goes to 3. So if 1 goes to 3, because we want to keep this a bijection, the only numbers that I can put here are 1 and 2. I cannot put 3 here or 3 here because it won't be a bijection. So the only numbers that I can put here are 1 and 2. So we can make one choice, which is say 1 and 2. And if we choose again to put a 3 here, then The only possible way in which we can fill out the rest of this row is 2, 1, because we already used 1 and 2. Remember, at all times, you have to make sure that this is a bijection. So we have a 2, 1 here. And that's all. That's all of them. Now, if you try to do some other way to fill out the second row here, you end up with the same arrays, probably in different order than the one you have here, but you will end up with the same basic things. So if you count here how many elements we have, so counting the identity, we have 6 elements in total. So what that means is that S3 will be the identity together with all these functions. Remember, these things here are functions. So this group of permutations of 3 elements has 6 elements in total. So that group has 6 elements. Now the binary operation here will be composition of functions. So whenever you operate one of these elements with another one, that will be a composition. All right. So that was an example for one particular case. Now, the way we ended up looking at all the elements is going to give us a way to count all the elements in the group. And that's the purpose of the next theorem. So let's look at this theorem here. So this is the order of Sn. So we're going to find how many elements this group is going to have. Now, remember that this bar here means number of elements. So the number of elements in Sn is n factorial, where that n factorial, remember, is the multiplication of all the numbers from 1 through n, like this. So it's 1 times 2 times 3 and so on. Okay. Now the reason I'm going to include this proof is because it has a nice idea about counting. Now, what are the elements of Sn? Remember that the elements of Sn are permutations or functions. So we are going to count functions. So let's read here the proof. So all the elements of Sn are bijective functions. That's just the definition of permutation. Of the form, the bijective function is a function that takes elements in the domain 1 through n, and it gives you the range 1 through n. The number of bijection, the bijective functions that can be defined on this, we can do it as follows. So we're gonna have a function that goes from 1 through n to 1 through n. So defining the function means I need to assign a value to 1 here. So what the function is gonna do here to the number 1. Now, this is gonna be counting a number of possibilities. Okay, so if you look at 1 here, in how many ways I can assign 1 to an element here. So 1 could go in through any of these possible numbers. So 1 could go through 1, 2, up to n. So in here, I'm going to put number of possibilities. So the number of possibilities here is n. Because it could go to 1, or 2, or to n. Now remember that we need to keep this a bijection. Because we need to keep this a bijection, once I choose where 1 is mapped or where 1 goes, that's going to restrict my choices for number 2. So for example, if I choose 1 to go in through, for example, 1, then 2 cannot go into 1 because I need to keep this bijection. So once I choose the 1 here, that's going to restrict my choices. I had n choices here for 1, but for 2, I will have n minus 1, because once I choose this one is going to leave me less choices. So the number of possibilities here, is n minus 1. And let me mark the ones here. So number of possibilities is n minus 1. Now I'm going to do one more, and you see the pattern here. So 3. Now I already chose 1 and 2 here. So 3 is going to have a restriction because 3 cannot be mapped into the same number that I mapped 1 and 2. So now, because I already chose the values for 1 and 2, I have to choose the 3 minus this 2. So I already choose 2 here. So the number of possibilities that I have for this one is n minus 2. So number of possibilities is n minus 2. And so that will give me the number of possibilities that I have for the number 3. So that would be n minus 2. Now you continue this way, and you see what happens here is every time I look at the number of possible ways in which I can map any number, it decreases by 1. So it's n minus 1, n minus 2, n minus 3, and so on. So if you keep going, the number of possibilities is going to decrease until you go up to 1. So here the number of possibilities will be 2, and here the number of possibilities will be 1. So then we have all possible values here. So we have n choices for 1, for 2 we have n minus 1 choices, for 3 we have n minus 2 choices, and so on for everyone here in the middle until you get to the last n. Once you get to the last n, you already chosen n minus 1, so you only can choose n to be only one choice here. Now all these choices here, for every choice that you make here, there is one choice that you can make here, and so on. So by the multiplication principle of counting, then the number of possible bijective functions on here is going to be the number of possibilities, the multiplication of all these possibilities. So if you multiply that out, the number of possibilities will be n times n minus 1 times n minus 2, and so on until you get to 1, and this is exactly n factorial. That's the definition of n factorial. That's gonna give me the number of bijections that I have from this set into this set. Then that means that's the number of permutation. So the conclusion here will be that, so therefore, let's write down the conclusion. Therefore, the number of elements in Sn, which is the collection of all the permutation on n elements, is n factorial. And that proves the theorem. Now, again, the reason I wanted to give you this proof is because it has a nice idea about counting. So at least now we know how many elements are in Sn. It increases really fast, basically. If you have, for example, 10 factorial is going to be a big number. Okay, one more thing I want to mention about this is that this group is called the symmetric group of order degree n. And we might refer to this group later like this. I'm just going to call it Sn. All right. One more thing I want to say about this is I'm going to compare this group with D4. Now, the group D4, remember, this is the group of symmetries of the square. So the symmetries of the square, D4. There's a good connection between this one and S4. So let me read that. So the group of symmetries of the square, D4, can be viewed as a collection of permutations of the elements 1, 2, 3, 4 by labeling the vertices of the square by 1, 2, 3, 4. So what do I mean by that? Now remember that D4 has 8 elements. So it has the rotations and it has the reflections that we talked about earlier. I'm going to recall that in this example. Now what I mean by labeling the vertices 1, 2, 3, 4 is, let's say you take the square here and I'm going to label it in this direction. So it's 1, 2, 3, 4. Now let's recall the elements of D4. So the elements of D4, let's start with the rotation. So rotation of 0 degrees, which basically is you take the square and you basically do a rotation of 0 degrees. Basically, you do nothing. If we represent if you label the vertices of the square by the numbers 1, 2, 3, 4 in this order, then what's going to happen with number 1? 1 will be fixed, 2 will be fixed, 3 will be fixed, 4 will be fixed. That will be the identity. So I can represent that with a permutation, which is basically the identity. So it's represented by the identity. So we are trying to represent every symmetry of the square as a permutation of 4 elements by labeling the square like this. Now, let me do this rotation of 90 degrees, which is counterclockwise. So we have the square here, and we're gonna rotate counterclockwise, which means we're gonna rotate in this direction, counterclockwise. If you do rotate 90 degrees counterclockwise, then the square is gonna look like this after you do the rotation. Now, how are we gonna represent that rotation of 90 degrees as a permutation? We're gonna see what the position of these elements go. So 1 will go into 1. So when you do the rotation, you see the 1 now moves here in this position. So we're gonna say 1 moves to the position number 2. So I'm gonna indicate that here. What happens with the number 2? When you do the rotation of 90 degrees counterclockwise, this 2 now moves in the position where 3 was. So move because of this one. 2 goes here. It moves from the position where 3 was. So 2 goes to 3. I'm gonna put that here. Let me do the other one. In this case, what happens with the number 3? So 3 was here, but when you do the rotation of 90 degrees, now 3 goes into this corner, so 3 goes to 4. Let's indicate that here. And let's see what happens for 4. 4 originally is here, but when you do the rotation of 90 degrees, 4 ends up in the position of 1, so 4 goes to 1. So this, remember, is just a representation. So this is an actual rotation of 90 degrees, and we can represent it by this permutation using the labels here of the square. You can do the same thing for the rotation of 180 degrees. I already did that. So for the rotation of 180 is represented by this permutation. The only thing you have to do is just follow here for 180 degrees. This is the original 1, 2, 3, 4, and then just see where 1 goes. So in this case, for example, 1 will end up in this corner, so 1 goes to 3, which is here, and the other ones are the same. Same thing, you can do the rotation of 270, which is represented again by a permutation, labeling here. You can double check that yourself. Let me do one of the flips here. So let's do the flip. So the H, which is a flip about the horizontal axis. So this will be the original square 1, 2, 3, and 4. Flip is rotation about this axis. So then if you see that, then this number 1 will move here. 4 will move here, and vice versa. 3 will move here, and 2 will move here. So you are doing a rotation, a flip about the horizontal axis here. So in that case, what's going to happen? So 1 goes to 2. So 1 goes to 2. And 4 goes to 3. 3 goes to 4. And 2 goes to 1. So that's what you see here. 1 goes to 2, 2 goes to 1, 4 goes to 3, 3 goes to 4 by doing this flip. I hope that was clear. The vertical axis, the flip about the vertical axis is very similar. So for the vertical axis, you rotate the original square, labeling 1, 2, 3, 4 like this. So this whole segment will now move here, and this whole segment will move here. So that's why 1 goes to 4, 4 goes to 1, and the other two elements just basically interchange each other. So 2 more elements of the symmetries of the square. So we have the flip about the main diagonals. Remember, these are all D elements, so we have only 8 for the symmetries of the square. Now D is the flip about the main diagonal, which is this one. This is what we call the main diagonal. Now if you flip about the main diagonal with these labels, these numbers 1 and 3 are gonna stay there because it's flip about this diagonal. So this 1 and 3 are gonna be fixed. So 1 will go to 1, 3 will go to 3. And what happens with 2 and 4 is they're gonna interchange places. So 2 goes to 4 and 4 goes to 2, as you can see here. So 2 goes to 4 and 4 goes to 2. And this something similar is gonna happen for the other diagonal. So in this case, this diagonal is gonna fix 4 and 2, like you see here, and it's gonna flip the 1 and the 3. Now, that's gonna be a representation of every symmetry of the square with a permutation. So that's an advantage of having a permutation, is instead of talking about geometrically about what the permutation does, you can talk about it as an array. So if D4 would start with, remember this is the symmetries of the square, is represented by permutations, there is even something more important here that I have to mention is the binary operation here of the symmetries of the square is concatenation of movement. So it's one. So for example, if you do D star D prime is the concatenation of the moments D and D prime. That concatenation of movement actually matches the composition of these two functions. So this representation is not only working geometrically in terms of the way in which you do the operation, when you do the concatenation of motions here, it also corresponds to the composition of the function. So if you think about it that way, then D4 is actually a subgroup of S4 if you label the vertices of the square by 1, 2, 3, 4. Now let's recall that the D4 has 8 elements, and how many elements do we have in S4? As we prove in the theorem, S4 has 4 factorial elements, which is 1 times 2 times 3 times 4, that's 24. So this set here, D4 has 8 elements, and this has 24. So this one is not the entitled S4. So S4 has permutations that do not correspond to symmetries of the square. So this group is of course a lot larger than D4. Now that's going to happen in general. In general, if you think about the permutations, the symmetries of the n-gon, which is Dn, so this is symmetries of the regular n-gon, and then you label again the same thing, 1, 2 through n. You can think of this as a subgroup of Sn. So Dn in general will be a subgroup of Sn, and they are not the same. So this has a lot more elements than the symmetries of the n-gon. That's a good way. The reason we talked about this is because it's a good way to represent the symmetries of the n-gon just by looking at permutations of elements from 1 through n. Alright, so that is all I have to say for today. In the next video, we'll continue with a little bit more of properties of permutations and some important theorems. Okay, that's all for today. Take care and good luck.